Welcome to our nocturnal laboratory of gentle discoveries. Here at Dreamtime Science, we transform complex concepts into lullabies for the curious mind. You know what's fascinating? I've been thinking about entropy, the way everything slowly moves from order to disorder, and imagining what it would be like if we could somehow reverse that process. There's something remarkable about the idea that if entropy went backward, time itself might flow in reverse, turning everything we know upside down in the gentlest, most mind-bending way. I'm excited to share what that could mean, not just in science, but in how we understand time and the world around us. Your support through likes and subscriptions keeps this tranquil laboratory of knowledge glowing softly. Tell me in the comments what scientific concept has always fascinated you. Now, take a moment, adjust your blanket, find the perfect hollow in your pillow, let your shoulders melt, breathe in and out. In the quiet hush of evening, when the mind softens and the questions of the day begin to flow like gentle streams through the twilight, there is a certain fascination that returns to us, one as old as memory, as persistent as the ticking of a clock. It is the allure of time itself, not merely its passage, but its direction, its relentless one-way journey from what was, through what is, into what will be. This is the puzzle of time's arrow, a phrase as poetic as it is precise, one that has haunted the dreams of philosophers, scientists, and storytellers for centuries. The arrow of time is not something we see exactly, but rather something we feel. It is the sensation of childhood drifting away, of old photographs fading, of a cup slipping from a careless hand and shattering into fragments that never, ever leap back together into wholeness. There is, in the fabric of our universe, a stubborn asymmetry, a preference for the forward march, an aversion to reversal. We do not see the spilled tea climbing back into the cup, nor autumn leaves reattaching themselves to bare branches, and yet our hearts long for the possibility. We dream of do-overs, of second chances, of the miracle of turning back the clock. It is no wonder, then, that our collective imagination has always been drawn to stories that dare to defy this one-way stream. In the flickering glow of science fiction, time becomes pliable, a thing to be bent or broken, to be traversed like a road or a river. We step into blue police boxes with the Doctor, swirling through eras as if they were rooms in a vast cosmic mansion. We climb into DeLoreans with Doc Brown and Marty McFly, chasing the paradoxes and perils that lurk in the corridors of Back to the Future. In these worlds, the fundamental rules seem negotiable, the arrow of time less an edict and more a suggestion. Yet beneath the shimmer of fantasy, there is a stubborn undercurrent, a principle that holds the real universe together. This is entropy, a word that carries the weight of inevitability, the whisper of decay, but also the subtle promise of understanding. Entropy is, in many ways, the silent engine of time's arrow, the reason that the past and future are not interchangeable, the reason that memories belong to yesterday and hopes to tomorrow. To grasp the nature of entropy is to begin to sense the true shape of time's arrow, not as a trick of the mind, but as a deep physical truth woven into the very fabric of reality. The word itself comes from the Greek en, meaning in, and trope, meaning change or transformation. In its earliest usage, entropy described simply the transformation of energy, the way in which heat, work, and motion are exchanged, and, in the process, how some of that energy becomes less useful, more diffuse, more spread out. In layman's terms, entropy is often equated with disorder, though this is a simplification. Imagine a child's playroom at the start of the day, toys neatly sorted, blocks stacked, books aligned. As the hours pass, play ensues, and the once ordered room dissolves into chaos, blocks scattered underfoot, dolls piled in a jumble, puzzle pieces lost beneath the rug. It is easy to understand this as increasing disorder, increasing entropy. What is less obvious but more profound is that the room could, in principle, become tidy again, but not by accident, not without the deliberate input of energy and effort. Left to themselves, the blocks will not restack. The puzzle pieces will not gather themselves into a perfect square. The tendency is always toward more possible arrangements, more randomness, more entropy. In the grand theatre of the cosmos, this tendency is everywhere. The hot coffee cools as its warmth disperses into the room. The ice cube melts in the summer sun, its crystalline structure succumbing to formlessness. Stars burn their hydrogen, fusing it into heavier elements, and in so doing release energy in a form that is less concentrated, more evenly distributed. The second law of thermodynamics, the great law of entropy, states this with unyielding clarity. In any closed system, the total entropy cannot decrease. The universe as a whole, it seems, is a kind of cosmic playroom, always moving from the neat, ordered arrangements of the past toward the sprawling, messy possibilities of the future. This, then, is the scientific underpinning of time's arrow, the asymmetry that arises because entropy increases. It is not that the laws of physics forbid time from running backward. Indeed, at the level of fundamental interactions, many of these laws are, by themselves, reversible. If you were to watch a film of two billiard balls colliding and then play it backward, you would be hard-pressed to tell which was the true sequence. The equations would work just as well in either direction. But as soon as you step into the world of many particles, of heat and energy, of molecules dancing in their trillions, the story changes. The odds vastly, overwhelmingly favor the direction in which entropy grows. The past is the low entropy state, the future the high. It is here that science fiction finds its deepest playground, for the question arises, what if we could reverse entropy? What if we could, by some technological marvel or cosmic accident, push the universe toward order rather than disorder, retracing our steps along the arrow of time? In Doctor Who, the Doctor often speaks of timey-wimey phenomena, of timelines that may be rewritten, of paradoxes that ripple and swirl through history. There are moments when the very flow of causality seems negotiable, where the past can be altered, the future remade. But even in these stories, there is a tacit acknowledgement of the danger, the strangeness, the near impossibility of such feats. When the Doctor contemplates reversing time, it is always with a sense of awe and risk, as if peering into the heart of the universe's most closely guarded secret. The reversal of entropy is not merely a matter of rewinding a tape. It is a reversal of the very processes that give rise to memory, to causality, to life as we know it. In Back to the Future, the DeLorean's lightning-powered leap through the years is thrilling, but it skirts the deeper truth, the improbability, the near impossibility of restoring the world to a previous state. Marty McFly's adventures hinge on fragile paradoxes, encounters with parents, near erasure from existence, the butterfly wing consequences of the smallest actions. Yet beneath the humour and excitement, there is an undercurrent of poignancy, a recognition that time moves in one direction for a reason, that to undo the past is to unravel the very web of causes and effects that shapes reality. These stories captivate us not because they offer simple escape, but because they illuminate the boundaries of possibility. They invite us to imagine for a moment what it would mean to live in a universe where time could flow backward, where entropy could decrease, where the arrow could be bent or broken. And in so doing, they sharpen our appreciation for the strangeness and beauty of the universe we actually inhabit. For in our world, entropy is not merely a force of destruction, but also a wellspring of creativity. It is the reason why eggs do not unscramble, but it is also the reason why stars shine, why galaxies evolve, why life itself can arise and flourish. The gradual increase of entropy creates gradients, differences in energy that living things can exploit, that engines can harness, that dreams can be built upon. It is a dance between order and disorder, between structure and chaos, a dynamic that gives rise to all that we know. And so, as we ponder the arrow of time, we find ourselves caught between longing and understanding. We long for the freedom to return, to undo, to relive, but we come to understand that the universe's preference for the forward march is not arbitrary, but essential. It is the foundation upon which memory is built, upon which hope stands, upon which all stories unfold. Yet the arrow is not always as smooth or as simple as it seems. In the quantum world, where particles can be in many places at once, where cause and effect become blurred, the nature of time grows even more subtle, more mysterious. There are hints in the mathematics of quantum mechanics that time's arrow might be less absolute than we suppose, that under certain conditions the boundary between past and future could become permeable, uncertain. In the vast and swirling cosmos, where black holes churn and the universe expands, the ultimate fate of time's arrow remains an open question, a riddle that science has not yet fully unraveled. Still, in the world of our everyday experience, entropy holds sway. The ice cream melts, the page yellows, the sandcastles crumble. We mark the passage of time not by the ticking of clocks, but by the increase of entropy, by the irreversible changes that shape our lives and our world. To understand this is not to surrender to despair, but to see more clearly the wonder and the poignancy of existence, the fleetingness of moments, the preciousness of order, the miracle of memory. And so, as you drift in the quiet spaces between waking and sleep, you may find yourself pondering the enigma of time's arrow. You may recall the stories that first kindled your wonder, the blue box that tumbled through centuries, the car that leapt across decades, the endless possibility of undoing and redoing. You may sense, beneath the surface, the deep hum of entropy, the silent engine that drives the universe forward. And you may find yourself wondering what lies beneath this arrow, what hidden patterns, what deeper truths. There are other worlds to visit, other questions to ask. The arrow of time, it seems, is just the beginning. As entropy unfolds, as the universe spins onward, the story grows richer, stranger, more beautiful. Somewhere in the depths of physics, in the tangled dance of particles and forces, there may be more to discover about time, about change, about the mysterious boundary between what was and what will be. The journey continues, and the mysteries of entropy beckon us onward, deeper into the unfolding tale of the cosmos. Now, let us drift deeper into the labyrinthine corridors of entropy, a word that, like many in science, holds a universe within its syllables. Entropy, a term that resonates with both the poetry of disorder and the precision of mathematics. It evokes dusty libraries of Victorian physicists, the relentless ticking of clocks, and the soft dissolution of order into chaos. But what truly does entropy mean to the world and to us? To begin, we must lay aside the popular caricatures, the ones that paint entropy as a villain, forever turning order into disorder, or as a metaphysical goblin that steals away the neatness of the cosmos. Entropy is, in its essence, a measure, a count, if you will, of the number of microscopic ways a system can arrange itself without changing its outward appearance. Imagine a deck of cards. When perfectly ordered, ace to king in each suit, there is but one way to be so. Shuffle the deck, and suddenly there are more ways, an astronomical multitude of arrangements that look disordered, even though to the cards themselves each arrangement is as real as any other. This, at its heart, is the scientific meaning of entropy, a measure of multiplicity, of possibility. Entropy quantifies our ignorance of the microscopic details, given only what we observe on the surface. The higher the entropy, the more ways the unseen components can be shuffled and still present the same face to the world. The lower the entropy, the more uniquely special the arrangement, the more tightly constrained the possibilities. But how did this somewhat subtle idea come to be associated with disorder and, more evocatively, with the passage of time? Let us walk back to the dawn of the 19th century, when the world of thermodynamics was being carved out from the mists of alchemy and steam. Here, in the era of steam engines and industrial revolution, entropy first found its footing. Sadi Carnot, a French engineer, peered into the heart of engines and asked why no machine could ever be perfectly efficient. Why must some heat, some energy, always be lost? In the decades that followed, Rudolf Clausius and Lord Kelvin wrestled with the mathematics, discovering that in every real process some energy is scattered, spread out, rendered less useful for doing work. Clausius, with the precision of a watchmaker, labelled this spreading out as entropy. To formalize, Clausius defined entropy as a quantity that always increases in a closed system. The famous second law of thermodynamics was born. In any spontaneous process, the total entropy of the universe increases. This was not merely a statement about the fate of engines or the efficiency of machines, but a profound pronouncement about the universe itself. In every transformation, ice melting, gas expanding, stars burning, the tally of possible microstates available to the system grows. The order of a single possibility gives way to the riotous freedom of many. But now, let us pause. The word disorder, often used interchangeably with entropy, is a metaphor, helpful yet misleading if taken too literally. The universe is not morally opposed to neatness, nor is it animated by a drive toward chaos for its own sake. Rather, the laws of probability are at play. When a system is left to its own devices, it is simply far more likely to be found in one of its many disordered states than in its rare, special ordered states. Consider a box divided into two halves by a partition, with all its gas molecules huddled obediently on one side. Remove the partition, and the molecules spread out, filling the box. The reason is not that they prefer disorder, but that there are overwhelmingly more ways for them to be scattered than for them to remain on one side. If by chance they clustered together again, it would not be impossible, only fantastically improbable, so improbable that the universe itself might age and cool 1 trillion times over before such a fluke occurred. Thus, entropy is the mathematics of possibility. It is the recognition that, for any system with enough parts, the overwhelming odds are stacked in favor of the many over the few, of the commonplace over the rare. This is not a law that requires an agent or a purpose. It is the quiet, relentless arithmetic of the cosmos. And yet, entropy is more than a tally of possibilities. It is also the silent metronome that gives direction to the river of time. The physicist Ludwig Boltzmann, haunted genius of the late 19th century, peered into the swirling dance of atoms and realized that the second law was not a commandment etched into the stone of reality, but a statement of overwhelming probability. Time, he saw, flows in the direction in which entropy increases. The past, that strange country, is memorable because it was more ordered, more special, less probable. The future, always unwritten, is a realm of greater possibility, greater entropy, greater uncertainty. Boltzmann's vision was radical. He proposed that the reason we remember the past but not the future is because the universe began in a state of extraordinary order, a low entropy state. From that singular beginning, the possibilities have multiplied, not because the universe is decaying, but because it is exploring the immense space of what could be. Each moment is a branching of possibilities, a proliferation of arrangements. The arrow of time, then, is not a thing, but a tendency, the drift from fewer options to more, from specialness to typicality. But here a question arises. If entropy is a measure of possibility, and if the second law merely states what is overwhelmingly likely, could it ever be reversed? Could we, through some cosmic or technological sleight of hand, make entropy decrease and thus turn back the arrow of time? Science fiction is rife with such reversals. Stories abound of machines that run backward, of broken eggs reassembling, of civilizations cheating decay and death. Yet, in the cold clarity of physics, the reversal of entropy is not forbidden, merely fantastically unlikely. The equations that govern the motion of atoms and molecules at their core are time-symmetric. If you were to watch a movie of two billiard balls colliding and then played it backward, the laws of mechanics would not protest. The reversed motion is just as valid a solution as the forward one, but probability is the great arbiter. If you release a drop of ink into a glass of water, the molecules disperse and the color spreads. Run the movie backward, and the ink would gather itself up, molecule by molecule, into a compact droplet. This is not impossible in the mathematical sense. It is simply so inconceivably improbable, given the number of molecules and the number of ways they can be arranged, that you will never see it happen by accident. The universe does not forbid order from arising spontaneously. It only stacks the odds so heavily against it that for all practical purposes it never occurs. Still, there are whispers of order arising from chaos, brief eddies in the current. In a small enough system, or over a short enough time, fluctuations can make entropy decrease for a moment. A handful of gas molecules might, by chance, all drift to one corner of the box. But as the system grows larger, these fluctuations become vanishingly rare. The second law is not absolute, but it is unyielding for anything larger than a microscopic speck. We must also resist the beguiling myth that reversing entropy would mean reversing time itself. The arrow of time, as we experience it, is intimately tied to the increase of entropy, but it is not identical to it. The world's equations, at their most fundamental, do not distinguish between past and future. It is only when we look at systems with many parts, with histories that can be lost or scrambled, that the irreversible flow emerges. Entropy is the compass, not the captain, of time's voyage. Suppose for a moment that entropy in some corner of the universe were to decrease. A shattered vase reassembles itself. The smoke from a fire gathers and flows back into the logs. Would time seem to run backward to an observer? Not necessarily. The observer's own memories, thoughts, and physiological processes are themselves caught in the current of entropy. To perceive time running backward, one would have to become backward as well, a thought as strange as it is unsettling. In practice, any local decrease in entropy is paid for by a greater increase elsewhere. The universe keeps its books meticulously balanced. This brings us to the subtlety of open and closed systems. The second law applies strictly only to closed systems, those that exchange neither matter nor energy with their surroundings. Life, for example, is a marvelous local reducer of entropy, building intricate structures and delicate order from the chaos of raw materials. But the price is paid in the waste heat and disorder expelled into the environment. The net entropy always increases. The living cell, the growing tree, the thinking brain, they are eddies in the flow, local pockets of decreasing entropy sustained by a greater, compensating increase in their surroundings. In this way, the universe is not a monotonous slide into disorder, but a rich tapestry of patterns, structures, and flows. Stars form from collapsing clouds, powered by gravity's relentless pull. Planets coalesce, life blooms, complexity emerges. Each local triumph of order is enabled by a greater global surrender to entropy. The night sky, with its galaxies and nebulae, is not a testament to entropy's tyranny, but to the creativity that flourishes within its boundaries. And yet there are limits to our understanding. The origin of the universe's low entropy remains one of the deepest mysteries in all of science. Why was the cosmos, at its birth, so exquisitely ordered? What mechanism, if any, selected that improbable beginning from the infinity of possible arrangements? Was it chance, a law we do not yet discern, or something stranger still lurking at the intersection of physics and philosophy? Modern cosmology, with its grand theories of inflation and quantum fluctuations, offers hints but not answers. The future, too, is shrouded in uncertainty. Will entropy continue its relentless ascent, leading to the so-called heat death, where all gradients vanish and nothing more can happen? Or do we misread the story, understanding only a fragment of the cosmic script? In the quiet moments between questions, entropy becomes less a villain and more a companion, a silent mathematical presence, guiding the transformation of the universe from its improbable beginning to its unknowable end. It is the reason you can mix cream into coffee but never unmix it, the reason memories fade and footprints vanish from the sand. It is the subtle script that underlies all change, all becoming, all loss and renewal. But as we close our eyes and let our thoughts drift, another question arises, gentle and insistent. If entropy is the mathematics of possibility, if it is the silent architect of time's arrow, then what of the exceptions? What of the improbable, the rare, the miraculous reversals that flicker in the margins of the universe? Is there a deeper pattern, a logic beneath the surface that we have yet to grasp? The mysteries linger, unresolved, like half-remembered dreams. And as the night deepens, we are drawn onward, ever onward, to the next threshold of wonder, where the story of entropy entwines with the fabric of information itself. In the deepening twilight of scientific thought, there flickers a peculiar fascination with disorder, a compulsion to trace the subtle footprints of entropy across the landscapes of nature. Few scientific ideas have so quietly infiltrated the boundaries of disparate disciplines, or so persistently challenged our intuitive sense of order and law. The journey of entropy is not just a tale of abstract equations and theoretical speculation, but a human story, a succession of minds striving to make sense of a universe laced with irreversibility, where time's arrow seems always to point away from order toward an ever-growing blur of possibilities. It began, as so many scientific sagas do, with careful observation. In the 19th century, the world was being transformed by steam, by the pistons and boilers of the industrial age. Engines roared, power was harnessed, and the promise of mechanical mastery was everywhere. But beneath the triumphant clangor, a quieter mystery troubled the mathematically inclined. Why could heat drive engines, but never be entirely converted into work? Why, after all the labor of a machine, did some energy always seem to slip away, lost not to the world, but into a diffuse, irretrievable warmth? Into this world stepped Rudolf Clausius, a German physicist and one of the first to give entropy its name and meaning. Clausius peered into the heart of the steam engine's paradox and saw a universal tendency, the tendency for energy to become ever more evenly spread, less able to do useful work. Clausius formalized this with a single, elegant equation. The change in entropy, ds, equals the infinitesimal transfer of heat, dq, divided by the temperature, T, at which it is transferred, ds x dq/t. But more than just an equation, Clausius's insight was a statement about the very nature of change. No matter how clever the engineer, some fraction of energy would always diffuse, entropy would always inexorably increase. What Clausius offered was a law as inexorable as gravity, but far more subtle in its action. He spoke not of force or acceleration, but of a hidden accountancy in nature, a cosmic bookkeeping that tallied not just energy, but the dispersal of energy. Through Clausius, entropy became the silent auditor of the universe, measuring the gradual loss of potential, the slow settling into equilibrium. Yet for all its power, Clausius's entropy was still a macroscopic creature. It described the fate of heat in engines and the limitations of physical processes, but left unanswered a more fundamental question. Why did entropy increase? What was it about the world at the microscopic level that generated this inexorable drift toward disorder? Enter Ludwig Boltzmann, whose restless mind and formidable mathematical gifts would forever change the way we think about nature's underlying rules. For Boltzmann, the answer was to be found not in the coarse averages of temperature and pressure, but in the teeming, invisible ballet of atoms and molecules. He imagined a world where each particle, seen or unseen, darted and collided in a frenzy of motion, obeying the strict dictates of mechanics, yet collectively giving rise to the smooth, predictable flow of heat and pressure. Boltzmann's great insight was to link entropy with probability. If you peer into a box of gas, you might see the molecules arranged in a neat cluster in one corner, or evenly spread throughout the box. The first arrangement is highly ordered, highly improbable. The second, vastly more likely. Boltzmann realized that entropy could be understood as a measure of the number of microscopic arrangements, what he called microstates, that correspond to the overall appearance or macrostate of a system. He captured this idea in a formula so simple and yet so profound that it is carved on his tombstone: S equals K log W, where S is entropy, K is Boltzmann's constant, and Borgu is the number of microstates. The logarithm, in Boltzmann's hands, became a bridge between the mathematical world of probability and the physical world of heat and energy. Boltzmann's approach was radical. Suddenly, the second law of thermodynamics, the law of increasing entropy, became not a mystical dictate, but a statement about probability. Systems move from less likely states to more likely ones, from order, which is rare, to disorder, which is common. The arrow of time, the one-way march from past to future, was written in the language of chance. But Boltzmann's statistical vision, as beautiful as it was, raised as many questions as it answered. For if entropy is a matter of probability, does that mean that given enough time, chaos might spontaneously reverse itself? Could the molecules in a room, by sheer chance, find themselves all huddled in one corner, leaving the rest of the room cold and empty? In principle, the mathematics said yes, but the odds are so fantastically low that for all practical purposes such reversals are never seen. The universe's arrow points forward, not because it must, but because the alternative is so improbable as to be, for human timescales, impossible. The tension between the microscopic reversibility of nature's laws and the macroscopic irreversibility of entropy would haunt generations of physicists. It was encapsulated in one of the most mischievous thought experiments ever conceived, Maxwell's demon, James Clerk. Maxwell, a Scottish physicist with a penchant for the playful, imagined a tiny creature who could see and control every molecule in a box of gas. This demon could, with a flick of a shutter, allow only fast-moving molecules to pass into one chamber, and only slow-moving molecules into another. In doing so, the demon would create a temperature difference without expending work, seemingly violating the second law of thermodynamics and reducing entropy at will. The demon's paradox was not just a puzzle for the mathematically inclined, it was a profound challenge to the very foundations of physical law. If the laws of mechanics are reversible, and if a clever enough being could manipulate the microscopic world, was entropy truly inviolable? Or was it perhaps a reflection of our own ignorance, our inability to track the comings and goings of countless particles? For decades, Maxwell's demon haunted the physics community, lurking in the margins of thermodynamics textbooks and philosophical debates. It was only with the advent of information theory, a discipline not of heat and motion, but of bits and messages, that the demon's secret was finally revealed. The key insight came from an unexpected direction, from a young American mathematician named Claude Shannon. In the mid-20th century, Shannon was not pondering steam engines or molecular chaos, but the problem of how to encode and transmit messages efficiently over noisy channels. He sought to quantify the amount of uncertainty in a string of symbols, to measure the information content of a message. Remarkably, the mathematical form of Shannon's information entropy bore a striking resemblance to Boltzmann's. It, too, was a sum over probabilities, a measure of possible arrangements. For Shannon, entropy quantified the average amount of surprise in a random message. The more uncertain or unpredictable the message, the higher its entropy. Shannon's work made it possible to prove theorems about the limits of communication, how much a signal can be compressed, how reliably it can be sent in the presence of noise. But it also hinted at a deeper unity between the worlds of thermodynamics and information. Information, it seemed, was not just an abstract concept, but had a physical footprint. It was tied to the states and configurations of matter itself. This realization provided the final twist in the tale of Maxwell's demon. In the 1960s, physicist Rolf Landauer pointed out that while the demon could, in principle, sort molecules without expending energy, its memory would eventually fill up. To erase the demon's memory, to forget which molecule went where, would require the dissipation of energy and the creation of entropy. The act of erasing information, Landauer argued, is a fundamentally physical process, and it restores the second law to its rightful place. The demon could not cheat the universe. Information, like energy, has a cost. Thus, entropy revealed itself not merely as a property of steam engines or gases, but as a universal currency of uncertainty, linking the material and the abstract, the physical and the informational. The second law of thermodynamics, once the preserve of engineers and physicists, now whispered its secrets to computer scientists, cryptographers, even linguists. As the 20th century unfolded, the concept of entropy began to branch out, sending tendrils into unexpected domains. In the study of life itself, biology, entropy became a lens through which to examine the delicate dance of order and disorder in living systems. Organisms, far from being mere passive passengers on entropy's one-way ride, actively fought against it, creating local pockets of order by exporting disorder to their surroundings. The cell, that tiny crucible of life, is a master of managing entropy, importing low-entropy nutrients, exporting waste, constantly maintaining the improbable order of living matter. In chemistry, entropy explains why some reactions go forward and others do not, why crystals form, why ice melts, why proteins fold into complex shapes. Entropy, alongside energy, determines the direction of chemical change, its increase marking the spontaneous, the natural, the likely. Even in cosmology, the fate of stars and galaxies is written in the language of entropy. The universe itself, once a hot, dense, low-entropy burst, is slowly unwinding, its energy spreading ever more thinly, its future marked by the heat death, when all gradients are spent and all differences erased in a uniform, chilly haze. But perhaps most surprisingly, entropy has found a home in the social sciences. In economics, the concept of entropy appears in models of market information and risk. In ecology, it measures the diversity and stability of ecosystems. Even in linguistics, entropy quantifies the unpredictability of language, the richness of vocabulary, the efficiency of codes. At each new frontier, the essence remains the same. Entropy is the measure of possibility, of uncertainty, of the number of ways things can be arranged. It is the silent counter of options, the auditor of chance, the bookkeeper of disorder. Yet, for all the clarity of equations and the certainty of experiments, entropy retains a core of mystery. It is at once a technical quantity and a philosophical enigma. It stands at the crossroads of determinism and randomness, of past and future. To study entropy is to glimpse the hidden structure beneath the world's surface, to see the universe not as a static tableau, but as a restless unfolding of possibilities. Scientists have devised ingenious experiments to probe entropy's elusive nature. In their laboratories, they cool atoms to near absolute zero, coaxing them into quantum states where the usual rules of thermodynamics are bent or suspended. They measure the entropy of black holes, where gravity and quantum mechanics collide, and discover that the surface area of a black hole's event horizon encodes the maximum possible entropy within. They build computers that approach the theoretical limits of information processing, seeking to balance the demands of speed, efficiency, and the inevitable cost of erasure. All the while, entropy continues its silent work, shaping the flow of heat, the growth of complexity, the decay of memory. Its footprints are everywhere, if only we know how to look. In the mixing of cream in coffee, in the spreading of ink in water, in the crackling static of a radio signal, in the birth and death of stars. And yet, as we follow the trail of entropy through the tangled forests of science, we are left with questions that shimmer just beyond reach. Is entropy truly an arrow, or merely a shadow cast by our own ignorance? Does the universe tend toward disorder, or toward new forms of order we have yet to imagine? In the next act of this unfolding story, we will step deeper still into the paradoxes and possibilities that entropy reveals, where time, information, and the very structure of reality entwine in a dance both beautiful and strange. There is a hush that settles over the universe when one contemplates entropy, a silence that is not empty, but dense with meaning. It is the hush of deep time, of stars burning out quietly in the cold reaches of space, of galaxies whirling in their majestic ballets, while the clockwork of disorder ticks on. Entropy, that subtle architect, is at once a destroyer and a creator. It is the gentle hand that stirs the tea and the restless force that wears mountains down to sand. Its whisper lies at the heart of every transformation, whether in the chaos of a supernova or the slow melting of a snowflake on a child's palm. To ponder entropy is to stand at the crossroads of physics and philosophy, to look not only into the equations that govern the world, but into the very nature of change, of time, and of meaning itself. For entropy is not merely a quantity to be measured in joules per Kelvin, nor just a tally of microstates hidden beneath the apparent calm of a system. It is a story told in the language of possibility and inevitability, an elegy for structures that must one day dissolve, and yet, for the briefest of moments, come alive with improbable beauty. Consider the heat, death of the universe, a phrase that lingers in the mind like a distant bell. It is more than a scientific forecast. It is a meditation on finality, on the limits of order, and the slow drift into uniformity. Imagine far in the future all the stars have burned their fuel. No more light, no more warmth, just a thin haze of particles, each carrying its own meager share of energy, spread so evenly across the cosmos that no work can be done. This is entropy's ultimate triumph, a state of perfect equilibrium, where nothing moves, nothing changes, and the universe is as close to stillness as the laws of physics allow. Yet to see this end is to misunderstand the heart of entropy, for it is not only about endings, but about the journey that unfolds before them. Entropy is the engine that drives the universe forward, that carves the arrow of time from the fabric of probability. The same principle that will one day dim the stars is the one that allows them to shine now. It is the reason we can look up on a cold night and see Orion blazing against the velvet dark, why the sun's fire can warm our faces and turn the wheels of life on earth. Without entropy, there would be no time, no change, no story. Let us dwell for a moment in the paradox that entropy presents. It is both the destroyer of order and the condition for creation. In the earliest moments after the Big Bang, the universe was hot, dense, and uniform, strangely a low entropy state, because the energy was packed so tightly that there were few ways to rearrange it. As the cosmos expanded and cooled, entropy increased. Structures formed, clouds of hydrogen, the first stars, the spiral arms of galaxies. Entropy, in its slow rise, carved out the gradients and imbalances that made complexity possible. It is because things fall apart that new things can come together. This interplay between order and disorder, between creation and dissolution, is not just a feature of the cosmos at large. It is woven into the fabric of our own existence, into the pulse of our hearts and the patterns of our thoughts. Every living thing is an island of order in a sea of chaos, a brief reversal of entropy's endless tide. Yet this reversal is only possible by borrowing from the universe's store of energy gradients, by consuming, metabolizing, and ultimately releasing more disorder into the environment than we forestall within ourselves. Take, for example, the humble act of breathing. With each inhalation, we draw in oxygen, fueling the combustion that powers our cells. This process, so vital and intimate, is a miniature engine of entropy. The sugars in our food, the air in our lungs, are reordered and broken down, their chemical bonds yielding energy and warmth. But this order is fleeting. The byproducts, carbon dioxide, water, heat, are scattered, their energy spent, their arrangement less structured than before. Our lives are a kind of burning, a slow and beautiful consumption, each heartbeat a note in Entropy's Elegy. Yet, within this inevitability, there is a strange kind of hope. Life does not rage against entropy blindly. It dances with it, harnesses it, even celebrates it. The tree that unfurls its leaves to the sun is not denying the laws of thermodynamics, but obeying them in a way that momentarily fashions order from disorder. The painter who mixes pigments, the poet who arranges words, the child who builds castles in the sand, all are part of this cosmic play, making patterns that are destined to fade, yet all the more precious for their impermanence. And what of the mind, the seat of consciousness, that most improbable of ordered systems? Every thought, every memory, is a configuration of neurons, a transient pattern of electrical charges and chemical gradients. The act of remembering, of imagining, is itself an entropic process. Energy flows, heat is released, connections are made and broken. Our very awareness is a local surge of order, bracketed on all sides by the march of entropy. When we ponder the universe, we are entropy reflecting on itself, a fleeting knot of order gazing back at the great unraveling. There is poetry in this, a resonance between the laws of physics and the stories we tell. The myth of Sisyphus, eternally pushing his boulder uphill only for it to roll back down, is an allegory for our condition. Yet, as Albert Camus wrote, one must imagine Sisyphus happy, for it is in the striving, in the act of making meaning against the backdrop of impermanence, that we find our purpose. Entropy does not render life meaningless. Rather, it grants each moment its weight, its poignancy, its urgency. Even our civilizations are footprints in the sand, rising and falling in waves of order and disorder. Cities grow, cultures flourish, technologies blossom, only to be eroded by the slow abrasion of time. Yet each act of creation, each work of art, each scientific discovery is a brief resistance, a shaping of the world against the grain of entropy, the cathedral, the symphony, the equation scribbled on a blackboard. All are echoes of our longing to leave a mark, to wrest beauty from the jaws of disorder. But in the end, entropy is not a villain to be vanquished, nor a curse to be lamented. It is the very condition that makes our universe dynamic, unpredictable, alive. Without it, the cosmos would be static, frozen in a single, unchanging configuration. There would be no room for surprise, for emergence, for the flowering of novelty. Entropy is the backdrop against which all stories unfold. It is the river in which we swim, the wind that fills our sails. There is a deeper mystery here, one that touches on the roots of time itself. Why does the universe have an arrow, a direction, a past and a future? Why are we haunted by memories, but never by premonitions? The answer, as far as we know, lies in entropy. The laws of physics, at the most fundamental level, are almost entirely time-symmetric. They do not prefer forwards or backwards. Yet, in our world, eggs break but do not unbreak. Fires burn but do not unburn. Lives are lived forwards and not in reverse. This asymmetry is a consequence of entropy's relentless increase, from the strange, low-entropy beginnings of the cosmos to its eventual maximal equilibrium. Thus, entropy is not merely a thermodynamic quantity. It is the arrow that pierces the heart of time, that divides what has been from what is yet to come. In its increase, we find the possibility of memory, of history, of becoming. The universe is not a static tableau, but a grand unfolding, a journey from simplicity to complexity, and one day back to simplicity again. And so, as you lie here in the quiet, perhaps listening to the hush of your own breath, consider your place in this unfolding. You are a pattern, a ripple in the sea of entropy, a brief crystallization of order that will one day dissolve back into the whole. But within that brevity there is grandeur. The atoms that make up your body were forged in the cores of stars, scattered by supernovae, gathered by chance and necessity into the intricate machinery of life. You are, in a sense, entropy's masterpiece, a fleeting eddy in the cosmic flow, aware of itself and its place in the scheme of things. There is a kind of solace in this realization. To embrace entropy is not to surrender to despair, but to recognize the beauty of impermanence. The cherry blossom that falls, the song that fades, the sunset that slips below the horizon, all are moments heightened by their transience. Without the shadow of ending, beginnings would have no savor. Entropy is the measure of what has been lost, but also of what is possible. It is the price we pay for the privilege of existing in a universe where anything can happen. In the quiet hours of the night, when the world outside is still and the mind turns inward, one can almost feel the pulse of entropy, the soft ticking of cosmic time. It is there in the cooling of the air, in the gentle fading of warmth from the pillow, in the gradual settling of thoughts as sleep approaches. Each moment is a passing, a letting go, a drift from order into the gentle embrace of disorder. Yet each moment is also a birth, a chance for something new to arise from the old. Perhaps, in some distant future, the universe will indeed go dark, its last embers cooled, its last patterns dissolved into the haze. But even then, the story of entropy will have been one of possibility, of stars born, lives lived, wonders made, and marveled at. The universe, for all its eventual silence, will have sung a song of change, of emergence, of fleeting beauty. And in this there is comfort, for to be a part of entropy's elegy is to be woven into the deepest fabric of the cosmos, to participate in the great dance of becoming and dissolving, of order rising and falling like the tide. We are stardust, yes, but we are also the shimmer of complexity, the brief luminosity that entropy makes possible. So let the thought linger as you drift towards sleep. Entropy is not the end, but the music by which the universe moves. It is the thread that links us to the stars, the breath that stirs the dust, the silent poet writing the story of all things. And though the song must one day fade, its echo will always remain, a testament to the beauty of change, the necessity of loss, and the glory of being, for a moment, alive in the great unfolding. As our journey through the swirling mysteries of entropy gently drifts to a close, may the quiet beauty of time's river, flowing ever onward, lull you into peaceful wonder. Like a comet tail fading into the hush of space, these questions invite us to dream beneath the stars, returning again for more whispered tales of the cosmos. Until then, rest softly in the embrace of the universe's endless quiet.